Hi, in this video series now we will talk about sequences or sequences in R, real number sequences. Sequences is a very important tool in mathematics and in other sciences, in all applied sciences. Let's say you go to a bank and the bank tells you if you deposit $1,000, you will receive tomorrow $100 as interest. So your amount will be $1,100, and then next day another $100, and the next day another $100, etc. Or this is option A. Or option B, if you deposit $1, tomorrow you will receive another dollar, so they will be 2, and then 3, and then 4, etc. In 100 days, which formula will be better for you? How do you do your calculations? Well, you use sequences, otherwise you wouldn't know. If you go to a bank and he tells you that if you take a loan, the interest rate will be 2% over 10 years, but as long as you pay your loan, the interest rate will be lowered because the amount remaining to pay is lower. Then how do you do your calculation to know in the fifth year how much you'll be paying as interest using sequences? So sequences are very, very important if a financial organization wants to make some statistics and try to guess what will happen in the market in the future, the prices of the market commodities or whatever, they will be using sequences. So sequences are really used everywhere, in computer science, in physics, in chemistry. There is this story about Gauss, who was a student. Maybe you heard about it. And his teacher told him he was upset of him for some reason. He told him, please go sit in the back of the class and get busy calculating the sum of all the integers between 1 and 100. So Gauss went to the back of the class and he didn't take any pen or anything. So the teacher said, what are you doing? You're not calculating the numbers. He said, yes, I already calculated them. And the teacher said, how? He said, yeah, the answer is 5050. And he said, how? He started calculating the teacher, and then he found that Gauss was right. And he took some time, but Gauss did it very fast. How? He was looking to the pattern. So sequences is all about patterns. And when I say pattern, I immediately think of the Fibonacci sequence. So maybe you heard about the Fibonacci sequence. The Fibonacci sequence is a sequence constructed as the first term is 1, and then the second term is 1, and then you add these two to obtain the term afterwards, it's 2, and then you add these two terms to obtain the one afterwards, it's 3, and then you add these two, then it's 5, and then it's 8, etc. And this sequence of numbers, you can find this pattern in really many applications. I will send you a document that you can read for your own information, just to see how the Fibonacci sequence or the Fibonacci numbers can be applied in many different areas, or can be found in many different applications. So sequences are basically a collection of numbers. Okay, they are put into boxes. So we have boxes, and in these boxes we'll put numbers like 1, 1, 2, 3, 5, 8, 9, etc. And then these numbers, they have indices, so they are indexed. So the first one is the box number 0, then the box number 1, then the box number 2, 3, 4, 5, 6, and etc. So any collection of numbers like this one, an infinite collection of numbers, is called a sequence. Now we have different type of sequences that we will study in this chapter. So you have usually the sequences that are interesting are the sequences where there is a pattern to follow. So the numbers in the boxes are not any numbers, they are numbers following a given pattern. And when they are following a given pattern, they are usually representing some physical problem. So we'll be interested in some already defined patterns, and we'll be interested also in this chapter to see what happens if you have a given pattern, not a very specific particular case, but a given pattern that can lead to some given numbers. So we'll be interested about the behavior of these numbers and where do they go. In fact, it's interesting to see what happens when you put a huge number of these numbers and then to see where these numbers go. What are they approaching? Let me take, for example, a very specific sequence. A sequence whose numbers follow a given pattern. Let me say, let n be the number of the box. So n is 0 or 1 or 2 or 3, etc. So for each box, the number inside the box will be 8 over 3n plus 1, sorry, 4n plus 1 and 4n plus 3 plus the box before. Okay, I will take this sequence for example. So mathematically we can prove, it's not your job to do it now, we can prove that if you take these numbers, the numbers that are calculating using this formula, these numbers will approach pi, that you all know. Okay, these numbers are rationals. Pi is irrational, so they are approaching pi. So as long as you go further, the numbers will approach pi. Let's look a bit at the calculation of these numbers. If I look a little bit at in here, so you have the box number is 0, 1, 2, 3, etc. And what I call un is the calculation of this 8 over 4k plus 1, 4k plus 3 plus the number of the box before. So the calculations will give, for the first box it's 2.6, for the second box it's 2.89, and etc. I continue the calculation to the box number 31, and as you can see, the numbers, they are increasing and they are approaching pi, you see. So I will continue with the boxes a bit further, arriving to the box 85. You see it's 3.13, so it's approaching pi, and I will continue. It's also 3.139, so it's almost 3.14. So we are really approaching pi. Now we are at the box 297. So it's interesting to see this kind of patterns where the numbers are approaching a given number. And as you can see, even if I go very far, I will never bypass pi, but I will be approaching pi all the time. So this kind of behavior, we will be looking into it also. When these numbers will be approaching a given number, which lead us to another interesting application of sequence, is the approximation of numbers. So if we don't know pi, that pi is equal to how much, we can calculate pi, or an approximation, a sufficiently close approximation of pi, using this sequence. If we calculate this pattern, if you go to the, I don't know, to the thousands, the box number 1000, we'll be having really a very close approximation of pi. Let's check it in here. Here we are at 369. I will go further. At the box 521, we are at 3.1406, etc. So I showed a little bit why sequences are important and how they can be applied. Now we will go to the theoretical lesson, where we can see how we will define mathematically sequences and what are the results that can be used and applied when using and when manipulating this kind of patterns or sequences. So mathematically, a sequence is defined as a mapping from n or an infinite subset of n into R. Okay, so it means that we take a mapping, which is a relation between AND and OR, and you will study the properties of mappings in algebra courses. So it's a mapping going from N to R, where to each N, which is the box number, we will give a corresponding image, which is U of N. If the mapping is U, the function is U. So U of N is the image of N, which will be the number in the box. So we can see the sequence as a relation, a function that takes in entry the number of the box N and gives us the number inside the box. So to each N, it corresponds U of N, which is the number inside the box. Of course, since the number of N's in big N are infinite, so the sequence is an infinite numerical sequence. It can go from N or from an infinite subset of N. It means that we can start by the box number 5 and go on. It's not necessary to start. It's not necessary to start with N equals 0. That's why we say that we can. It can be defined from an infinite subset of N instead of N. So we will denote by UN U of N. So when we say UN, we mean it's the image of the box number N, which is the number inside the box number N. So UN will denote the general term of the sequence. I mean by this that if I say UN equal N plus 1, it means that for the box number 1, if the box number is 1, then the number inside the box is N plus 1, which is the number of the box plus 1. So inside we have 2. For the box number 5, inside we have 6, and so on. So the sequence itself will be denoted UNN. When I say UNN, it means that I'm talking about the sequence. When I say UN, I will be talking about the general term, which is the term, this one, that gives the value at any given point N. So it's the general term that represents the relation or the formula that should be used to calculate the number at a given position N. Okay, so now U0, it's the content of the box number 0. U1, it's the second element of the sequence, which is the content of box 1. UN, the content of box N, which is the nth element of the sequence. So here is another example, UN equal minus 2N plus 1 over N plus 1, which means that U5 will be equal the content of the box number 5. It will be minus 2 times 5 plus 1 over 5 plus 1, which is equal to minus 10 plus 1 minus 9 over 6, for example. This is the content of box number 5. Now I will use this kind of representation, to show the shape of a given sequence to understand its behavior. So here I will represent the number of the box, let's say the N, the index N. I will not be using number of box later on. From now on I will be using the index N. So here I will show the index N, 0, 1, 2, 3, etc. And for each index N, I will show the value of the element of index N. So for 0, we have U0, which is here around, I don't know, 0.3. U1, which is around 0.1, etc. Okay, so U1, U3, U4, U5, there is no U2 in here. So this is U2, U3, U4, and then U5, etc. Here you have U15. You see 15 in here. It's down there. It's not up there. So it's a minus. And then U16, it's in here. U17, it's down there. U18, U19, etc. Now I say that a sequence is bounded above if all its elements, even the farthest ones, if you go really very far, all the elements will be always below a given value. So there exists M belongs to R such that for any element or for any integer n, un is less than m. So all the elements of the sequence are less than a given number m. If this is the case, then m is an upper bound of the sequence. Of course, if m is an upper bound, then there exist other upper bounds, all the numbers that are greater than m. So then m is an upper bound of the sequence and all the elements are less than m. And also I say that a sequence is bounded below if all the elements of the sequence are greater than a given number in R that exists. And then I say that a sequence is bounded if it's bounded above and bounded below. So let's say that it's bounded above, then there exists m such that un is less than m. If it's bounded below, then there exists small m such that un is less than m. If it's bounded, then there exists m and there exists m, a big M and a small m, such that un is between m and m, right? But to simplify the definition of bounded, look, if big M, for example, it's 5 and small m is -1, couldn't we say that un is between 5 and -5? Why not? Because if it's greater than -1, then it's greater than -5. So, which allows us to write that un in absolute value is less than 5. And this is a nicer representation than this one. So we say that there exists a number, which is 5 in this case, such that the absolute value of un is less than 5. This can always be done. We can always choose the same number and say that the absolute value of the elements of the sequence are less than this number, instead of saying that there exists big M and small m. That's why if a sequence is bounded, then it's bounded above and bounded below. Then there exists a number that I call here k, such that un in absolute value is less than k. Now, going back to the example I gave in the beginning of the chapter about Gauss, when the teacher asked him to calculate the sum of all the integers between 1 and 100. So it's basically 1. So it's 1 plus 2 plus 3 plus etc. plus 100. And I said it's all about looking at the pattern. Of course, you can calculate this sum by saying, yes, it's 1 plus 2, it's 3, 3 plus 3, 6, and then so on to arrive to 100. It will take you like 20 minutes to finish. But you can also look at the pattern, saying that, okay, here I will write like 97 plus 98 plus 99 plus 100, right? So you can see that if you take the first element and the last one and then you add them, you will obtain 101. And then if you take the second term and the one before the last one, it's 2 plus 99, it's 101. And the third term and the one before 99, it's 3 plus 98, it's 101, and so on. So you have always 101. So all you have to do is take 101 and multiply it by the half of the numbers of by half the number of the elements. Okay, so this kind of pattern is interesting. Why it works in here? It works because this sequence is constructed starting by 1 and then adding 1 at each step. Then plus 1 you have 3, plus 1 you have 4, etc. So it's the same number that you are adding at each step, and this is what this particularity that it gives us the pattern that we observed in here, and this is how Gauss calculated the sum. So this kind of sequences, we call it arithmetic sequence, when any number is obtained by adding to the number before it a given constant, the same constant at each time. So an arithmetic sequence is a sequence where numbers are obtained such that the difference between any two consecutive terms is constant. So any two numbers that are consecutive, the distance between them is the same as all the time. So this constant is called the common difference, and it's denoted D. Now, something interesting about the sequence is that if I tell you that the first number is 1, and then the common difference, so U0 is 1, and the common difference D is equal to 3, which means that the first number is 1, the second one is 4 because it's 1 plus 3, then it's 7, then it's 10, etc. My question is, can you calculate U10, for example, the 10th term? If you are starting, no, we are starting by 0, so it's the 11th term, U10. Can you calculate the 11th term, U10, without calculating all the terms? Yes, of course, because it's equal to the first term plus how many times I added 3 to arrive to the 10th term. So I added 3 in here to obtain U1, and then I added 3, I obtained U2, and then I added 3 to obtain U3, etc. And then when I add 10 times 3, I will obtain U10. So it's 1 plus 10 times 3, which is 30, and then it's 31. Okay? So this kind of formulas is important because it allows us to make very easy calculations for very far numbers. Even if you want to calculate U100, U200, you can do it very fast. That's why we write that any number UN is equal to, this is nothing bullet in here, so any number UN is equal to the number before UN plus 1 plus D. So let me insist on what's written in here. When I say UN, I mean it's the content of the box of index UN. When I say UN minus 1, it's the content of the box of index n minus 1. So it's the box right before UN, or the box number n, right before the box number n. Okay, so how you should read this formula? You should read it like this. You should say any box is the box before plus D. Okay, and it can be applied to any box. So if n is equal to 1, this formula will be U1 is equal to U0 minus D, plus D, sorry. Or if you write it U5, it will be equal to U4 plus D, etc. So n minus 1 represent one box and the one before. Or, of course, I will take the last one. UN is the first element plus n times the difference. This is what I have done in here. So if you want to obtain U10, it will be the first term U0 plus n times n. The n in here is the same n in here. Okay, so it will be plus, since n in here is 10, so it's 10 times D. Okay, so this can be used to calculate U10 if you already know U0, which is the first term, denoted U0 in this case. Okay, so what about if you want to calculate U10, but you don't have U0, you have U5, the fifth term, and you want to calculate the 10th one? So then you will check how many times I'm adding the common difference from U5 till U10. It's 10 minus 5. Okay, that's why we write this formula, which is any term UM, it's equal to any other term UN plus D times the difference between M and N. So it means that U20, for example, if you want to calculate U20 using U5, it will be U5 plus the common difference D times 20 minus 5. And this is really very, very important. Okay, now if I clean a little bit in here, so this is nothing. Now also what's interesting is the following. If I want to calculate the sum of n terms, like from u0 to un, for example, u0 plus u1 plus u2 plus u3 until un. I will take the first term and the last term as I did for the example of Gauss. So I took 1 plus 100, it's 101, and then 2 plus 99, it's 101 as well, right? So I take the first one and the last one, which will give me the 101, okay, and then I multiply it, this is it, I multiply it by n plus 1 over 2, which is the half number of that terms, because from 0 to n we have n plus 1 terms, and then I will multiply u0 plus un by half number of the terms, because u0 plus un already gave me the sum of any two terms, like the first one, the last one, plus, or the second before the last one, etc. Okay, so these formulas are to be known, they will be used widely, the formulas of the arithmetic sequence. Now, if we go to the geometric sequence, in the geometric sequence, it's a sequence where we obtain each term by multiplying the term before by a given constant. So it's a multiplication now by a constant, not an addition. So we have a bit similar formulas. Now, each term is equal to the term before times q, or r, it should be r in here. So this is, it's denoted r, and it's called the common ratio. It's the number by which I multiply each term to obtain the term afterwards. So un is equal to un minus 1 times r, or un is the first term times r to the power n. So I multiply by r, I obtain the term after, and then by r another time I obtain the term after, and so on. So un, if you want, if I say it's equal to u0 times r to the power n, it means that if you take u0 times r, this will give me u1, and then if you take another r from here, so it will be r minus 2, so this will give me u2, and etc. So if you multiply by r n times, you'll obtain un. And also I will write the formula that will give me any term, function of any term. It's um, like u100 equal to u10 times, this is r as well, times r times m minus n, which is the number of times I'm multiplying by r to go from un to um. What's more also interesting is to calculate the sum of n terms of the geometric sequence, which is u0 plus u1 plus u2, etc. until un. So it's equal to u0 times, so this goes in here, I will remove it from here, u0 times 1 minus r to the power n plus 1 over 1 minus r. So this formula will give the sum of the numbers that are constituting this geometric sequence going from 0 to n. Be careful though that the n plus 1 in here, you should not read it as n plus 1, you should read it as number of terms. So here, because from u0 to u1 we have n plus 1 terms, so n plus 1 in here, it will represent the number of terms. So if you, for example, calculate u1 plus u2 plus u3, it will be equal to u1, the first term of these numbers, times 1 minus r to the power number of terms, which is 3 over 1 minus r. Okay, so we should really read these formulas not in their the way they are written as n and etc. You should read them as what they represent, or what n and m represents. Okay, so here n plus 1 is really the number of terms.